Math 2415, Calculus 3, Section 13.5, Curl and Divergence, video 4 out of 6. We're halfway through this series of videos for 13.5, and we're going to start talking about divergence now. Divergence of a vector field, which we're using capital F of the vector field, whose component functions are P, Q, and R, so we're still talking R3, is, well, here's the definition. The divergence of F, abbreviated div, is the partial of P with respect to X plus the partial of Q with respect to Y plus the partial of R with respect to Z. Now, upon first glance, you might think that's just the gradient, isn't it? Well, no, for two reasons. Number one, when you do gradient, your three partial derivatives are all of F, not its component functions. Excuse me. When you do gradient, you take the gradient of a scalar field, and so all three of these are just the same function, F, F, and F. Secondly, gradient is a vector field, meaning its results as a vector. Divergence is a scalar. No components, just partial with respect to X plus partial with respect to Y plus partial with respect to Z. Now, one thing I do want to point out is that even though this is a pretty simple formula to remember, or definition to remember, you can write it a little bit more compactly if you take advantage of the Dell operator vector, because this almost looks like a dot product. If you thought of it as the Dell vector operator, so partial X in the first component, partial Y in the second component, partial Z in the third component, and sorry, my little deltas are looking like 2s, I'll try to fix that. And then take the dot product with P, Q, and R. Well, dot product just means first product plus second product plus third product, except in this case, product means partial derivative of. So we could rewrite divergence as the Dell operator vector dot F, which is really kind of convenient because curl is just cross product. Curl of a vector field F was Dell vector operator cross the vector field F, whereas divergence of F is the Dell vector operator dot the vector field F. And again, divergence is a scalar field, so the result you get is a scalar. But what does it measure? The curl vector, curl of F, this is a vector, gives you an axis of rotation and, well, actually gives you the tendency to rotate around an axis of rotation. The axis of rotation is intimately related to that angular velocity, as we saw in the first video. But what does divergence measure? Divergence measures the tendency in a vector field for objects to be pushed away from a certain point, to diverge from a certain point. The way the author phrases it, and I'm just going to read to you, I hate just reading in videos. The reason for the name divergence can be understood in the context of fluid flow. If F is the velocity of a fluid or a gas, then divergence represents the net rate of change with respect to time of the mass of fluid or gas flowing from the point per unit volume. In other words, divergence measures the tendency for fluid or gas to diverge from a given point. Now, I forgot to mention this back in the curl videos, but if curl is 0, that means that there's no tendency to rotate. So when curl is equal to 0, that is called irrotational, because there is no tendency to rotate around that axis. When divergence is equal to 0, and it would be the number 0 because divergence is a scalar field, not a vector field, this is called incompressible. Incompressible. Meaning that your fluid or your gas is not being compressed in some certain direction. Incompressible. I believe it is yes, incompressible. But actually calculating divergence is pretty trivial. For example, I do have an example set up, right? I thought I did. Well, let's take a look at an example. Let's say our vector field F is given by the function, let's see, or by the scalar field. First component is, oh, it's this guy again, xz second component is x, y, z, and third component is negative y squared. Let's just calculate divergence. Divergence of f is just partial with respect to x of the first component, so partial with respect to x of xz, plus partial with respect to y of the second component, xyz, plus partial with respect to z of the third component, which is negative y squared. Well, this is pretty easy. The partial derivative of xz with respect to x is just z. The partial derivative of xyz with respect to y is xz. Remember, in a partial derivative, all the other variables are like constants. Speaking of which, the partial derivative of negative y squared with respect to z is 0, because with respect to z, negative y squared is a constant. So that was pretty quick. But let's follow this up with, is f incompressible? Which is asking, is the divergence of f equal to 0? Well, no. Because z plus xz is not always 0. We could find conditions which would make it be 0, put that equal to 0 and say solve it for z or solve it for x. But in general, x plus xz is not always equal to 0, so f is not incompressible. It may be incompressible at certain points, but not at, so there are certain points that are not pushing fluids away. For example, at the origin, where x and z would both be 0. In fact, anywhere on the y-axis where x and z would both be 0, then this particular vector field would be incompressible, meaning that no point on the y-axis is pushing fluid away from it. All right, so that was pretty straightforward. I thought there was more in that video than that. I guess not. Yay, short video.